two-roll mill, okay? And we said that when mixing rubber, we combine rubber with different types of additives, such as sulfur and generally some other chemical agents that help for the creation of chemical crosslinks, okay? In the case of the rubber, we already discussed, and we will be discussing extensively on Thursday, that these crosslinks are very weak, okay? Of the secondary preforms that are also heated up at temperatures higher than the glass transition but lower than the melting point, and then again we blow air. And fiber spinning is very important because we generally create very high performing materials. And why we create high performing materials is because the fibers that we produce have very high orientation, very high chain orientation. We achieve that by stretching the fibers through very thin spinnerets, okay? But also we can do we can further orient the chains after we do the fiber spinning. So it can be a two-step process. We firstly orient them as much as we can through fiber spinning, and then we do the drawing process, okay? That is the post-processing that I write here. The drawing process can be either in helped by temperature, or it can be done in room temperature, okay? We do not need to absolutely use temperature in order to do the post-processing. Post-processing, essentially what we do is we take the fibers and we slightly pull them, okay, in order to make the chains orient, but we don't want to cause a permanent deformation, okay? And that is why we need to be very careful on how much we stretch them after fabrication. We have different types of fiber spinning, such as melt spinning, where we spin the melt, or dry spinning, where we essentially spin the polymer that is dissolved within a solvent. In this case, the dry refers to what happens to the dissolved polymer after it comes out of the spinneret. And in this case, we use temperature for solvent evaporation. Yeah, these are some examples on essentially the performance and the characteristics of oriented materials, such as polyethylene, which is a very common material we use for the fabrication of high-performing fibers. Usually, as we said, it's ultra-high molecular weight polyethylene that performs the best, and that is because the chains in ultra-high molecular weight polyethylene are very large in number, but also large, okay? And because they're large in size, if we manage to orient very long chains, we achieve even higher degrees of crystallinity. And because we have very high degrees of crystallinity, a high orientation, what kind of properties do we get? We get excellent mechanical properties, excellent thermal conductivity, what else? And anti-corrosion. Essentially, 1R. Very characteristic applications of high-performing fibers. If we want to create very tiny fibers, we use that electro spinning process. As I told you, I don't want you to remember how these processes take place, but I want you to remember what kind of materials are produced by these techniques. And electro spinning fabricates nanofibers, okay? Very, very thin fibers. The trick with the electro spinning is the difference in voltage between the spinneret and a collector, okay? And because of this difference in voltage, we form this very highly charged liquid. This liquid jet here is highly charged. Because of delta V. And in this case, because it's highly charged, essentially the fibers are deposited with very high speed onto the collector. And because of the very high speed and very high pressure at the end of the spinneret, we create these very thin and very small fibers. So you can see how small these are, okay? These are nanofibers. And we went on to discuss injection molding, okay? We already said that injection molding is the second most popular polymer processing technique, along with extrusion, okay? And we will see again today how injection molding takes place. It is very similar in the beginning of injection molding because it's very similar to extrusion, the beginning of injection molding, where essentially we need to melt our polymers, and after we melt our polymers, we make them travel through an initial part of the injection molder, and we inject the melt onto a mold, okay? After we inject our melt into the mold, the mold is very completely packed, okay? We fill the mold completely, and then we cool down the mold. After we cool down the mold, the material is solidified within the mold, and we open the mold and we take our product out. We will discuss today why these materials, injection molded materials, have a skin core structure, okay? It's a very characteristic, let's say, property of injection molded materials. And yeah, this is how an injection molder looks. We said that the polymer is melted here in this region, and the screws travel back and forth in order to fill the mold, okay? And once they fill the mold, we close the barrel, we stop squeezing polymer within the mold, then we control the temperature of the mold, we cool it down, and once it's cooled down, we open the mold and we take our fabricated material out. It is very important to distinguish different types of injection molding machines, and we said that for extruders, the distinction comes over the length to diameter ratio of the screws. Or screw, because we can have a single screw extruder. In the case of injection molder, we need to know the tonnage, okay? The tonnage is the amount of clamping force. That is how much injection pressure we induce to the mold, okay? And that is the injection pressure times the cavity area of the mold. These are some very simple injection molded products. You can see that we can create from very simple to, they're not depicted here, but we can create highly complicated shapes from injection molding. But the most important part in injection molding is to have a very accurate, let's say, mold that reflects on the material that we want to fabricate. Now, this is not that important, but in order to increase the bending stiffness of materials that are injection molded, we use this technique that is called ribbing, okay? So we create these internal structures here. You can see these are all plastic. This material was, without this, if a certain load was applied without the rib, it will break much easier, okay? Ribbing generally increases the moment of inertia and the bending stiffness, okay? So we use these features here essentially, or like these ones and these ones, okay? Which help the material not to break under low stresses, okay? It's not that important. And let's have a look once again what happens in an injection molding sequence. Again, we say we fill our polymer pellets here. The temperature is generally higher than the melting point, so we ensure that we have a completely molten material. And once our material is completely molten, we close the mold and we inject our material forward. Okay? After we inject our material forward, the cavity of the mold fills with a polymer. Okay? We pack the material. We pack by keeping our screw at the same point in order to ensure that the mold is completely full. We need to ensure that the mold is completely full, because if not, we will have processing problems and our ultimate material will not be the one that we want, okay? And then we cool down the mold and the screws retract. We wait in order to cool down the mold, and once the mold is cooled down, we can open the mold in order to inject the material, and the screws, after they retracted, they're ready for another cycle of injection molding by pushing the melt into the mold, okay? And you can realize that this happens multiple times throughout an injection molding sequence. So in this case, we fabricate multiple materials just by pushing the polymer within the mold, cooling down the mold. So this process of cooling down is very important. And essentially, cooling down guides how fast our injection molding sequence takes place. Generally, injection molding is very fast, okay? But the most time-consuming process is the cooling down of the mold, as we need to ensure that the polymer is completely solidified within the mold. Let's have a look at the final video, I think, for today, for this section. Stop sharing. We will see how injection molding takes place, essentially. PowerPoint. Okay. There it is. It's better to show you in 3D because it's more obvious what's happening, okay? So what happens if we want to create this relatively simple finish plastic part? This is the mold, okay? You can see that there is one side of the mold that is moving and one that is stable. This is how injection molding machine looks. Similar to the extruder, we have a gravity-fed pellets, we have the heating elements, we have the screws. In this case, we have only a single screw, okay? We don't need to have two screws in order to mix anything. So this part is very similar to a single screw extruder. Yeah, there is a connection with coolant materials in order to make sure that the polymer is completely cooled after it fills the mold. We cool it down. Okay, wait a second. This part here where we have retracted the screws, it's called dosing, okay? So the screws go to the back, and then there's polymer over there at the front, which is ready to be filled, to fill the next product once the mold closes again, okay? So you can see, after it's cooled down, we have this dosing where the screws retract. We inject our part by the moving platen, and then we repeat the process again. So you can realize how fast this process takes place, depending, again, I repeat, on cooling. This is how an injection molder looks. We need to be controlling accurately both pressure and temperature, of course. And now let's go back to the slides. share. Yeah. I hope you can still hear me. Yes, we said about the clumping force, okay? It is a way of characterizing the size of an injection molder. And let's have a look at what happens. Let's have a look at what happens in an injection molding cycle. When we sketch the graph of pressure over temperature. So we have the pressure, let's say pascals. I repeat again, please, in the exams, in all graphs or whatever you use, please remember to use units, okay? It's a silly way to lose points out of your final mark by forgetting to use units. And let's say we have the time here, terms of seconds. Yeah, I said pressure over temperature. No, it's pressure over time. So here's the count pressure. So the pressure in terms of how it evolves during an injection molding cycle is a graph that looks like that. Okay, and essentially it consists of different areas. Okay, in this first area where we have this small peak here, where essentially the pressure increases initially, is a part that is called fast casting, and essentially during this part the polymer starts to melt. Okay, sorry. And once the polymer starts to melt and is turned within the screws, the pressure starts developing. Okay, so here, how the polymer along the screws. After that, as we can realize, we need to fill our polymer, and that is when fill our mold with polymer, and that is when the pressure increases very significantly, because we need to ensure that the mold is completely full with polymer melt. Okay, so up to here, this part is called filling or filling of the mold. Okay. Then, once we filled our mold, we don't need to push even for more material, so the pressure has reached its maximum, and then we need to reduce it slightly and keep it at the same pressure while we're cooling it. Okay, so in this case we do what is called the packing. So up to this part we have the packing, and finally this region we can have the part ejection. Okay, that is how an injection molding cycle looks like in terms of pressure. Generally, I told you that injection molding cycles are relatively fast. An average time of injection molding takes, an average cycle of injection molding takes place around 35 seconds, or 25 to 35 seconds. And generally, the difference between packing and part ejection is around 2 seconds. So this should be around 33 seconds. Okay. This is how an injection molding cycle looks. Now let's go back. Yeah, let me show you, sorry, let's go back. And let me characterize also what's happening. Let me move this here. And let me also move this as much as. Anyway, okay. So this, in general, the whole region here is called the cycle time, okay? It's very obvious. This part here, okay, shows the time at which the mold is closed, okay? So the mold is completely closed and we fill the mold with polymer. So this, in this time, we have a mold closed time, okay? And this time here, essentially is the cooling time. Okay? Now, in terms of the pressure, in terms of the temperature, only look at this graph here, the red one. The dotted one is not that important. It's just before the mold, but we don't really care too much about that. As you can realize, in the beginning we keep the temperature relatively constant, and then when cooling, we reduce significantly our temperature. Now here they're saying that we eject at 100 degrees, but I wouldn't say that this is a wise choice. This temperature needs to be in the order, I don't know, to 40, 50 degrees in order to be able to handle them afterwards, okay? Because if it's around 100 degrees, the polymer will be generally very warm, okay? And if it's very warm, it can still be scratched, be generally affected by any external factors, okay? So we need the temperatures to be very low in order to be handled and fully solidified. Okay. This is more straightforward than the injection pressure. No, here we don't have the pressure, we have the temperature. Now, when we're processing by injection molding, there is a certain processing window that we always need to be operating within this window in order to ensure that we have a fine product, okay? A good performing product. And let's have a look at the different parameters that affect the processing window. Here we have a graph of temperature over pressure, okay? So let's have a look at the first, at the left side of the processing window, where we have this problem that is called short salt, okay? If we operate at pressures lower than this pressure here, this range of pressures, okay, we are within a low pressure region. So let's say in this region we have low pressure, okay, and a short salt essentially means that there is not enough material that is injected. So that can be an effect of the speed of or the pressure of the injection molding is too low, or the mold is too cold before the polymer comes in the mold. And in this case, you can see that we don't have completely full fully developed material. Okay, these are essentially lack of material. So short thought is because we don't have enough material that is injected into the mold, we have low injection speed, okay, but the speed essentially is related to the pressure, which is the most important. So the pressure is too low, so we didn't inject enough polymer within the mold, or the mold was too cold, so it didn't accept all the material that it could. Now, thermal degradation is also very important. If we use processing temperatures that are higher than the degradation temperature, then our polymer can degrade, okay? So if we are within this range here, we are already at very high temperatures, and because of very high temperatures, we can have significant problems in terms of performance. When we have visible, it can look like that when we have black spots or burn marks. Okay, this is how it can look. Now, flash is another let's say problem with injection molding, where in this case the mold is overpacked, or we have too much speed or material injected in there. And because we have too much material injected in there, then the material looks like that, okay? In the simplest cases, in the most easy cases, we can simply cut these materials, okay? So in an academic laboratory, I've done it several times myself. I've overfilled our mold, okay? By overfilling the mold, you end up having these materials. And then in an academic environment, you just cut them with a scissor or whatever. But in an industrial environment, you cannot essentially deal with these on a one-by-one case, because you're producing so much materials. So you don't want that. So flash takes place when the mold is overpacked, or we have too much injection speed or material. And finally, melting, if we have not, in this case, we have low temperatures. In this case, we have not completely melted our pellets, okay, our granules, and this is how the material is looking there. These are unmolten polymer pellets, and these materials are called fisheye materials because they have some very small dots over there. Okay, so in this case we have too low temperatures. Yeah, this is how an injection molding cycle looks. Once again, I told you in around 4 seconds we have the filling and the closing of the mold. Here I told you injection molding time takes usually place 25 to 35 seconds. Okay, so you can see that we have around 4 seconds in order to fill the mold. Okay, then in order to ensure that our material is very nicely packed and the pressure is constant on the mold, we have the pack and hold cycle. Okay, we have the pack and hold process, which takes place in around 8 seconds. And as I told you, cooling is very important. We need to fully cool our polymer in order to take out the best material that we can. So this, in a 25-second cycle, takes place in around 11 seconds. Okay, so you can realize once again that cooling is the most time-consuming part. These are how molds look. Essentially, they can be very complex, and they're typically quite expensive to fabricate. Okay, these are very simple molds in order to fabricate plastic spoons. Okay. Yeah, let's not focus too much on the molds. Now, I told you in the beginning that we have this skin core structure in our in our injection molded materials, okay? Skin core structure. And what does skin core structure mean? It means that we have slightly different characteristics in terms of our material properties. If we fabricate, let's say, a rectangular material, the skin is this part here, where essentially our polymer touches the walls of the barrel. So skin is this part here, and core is the inside of it, okay? Now, as you realize, when a polymer in its melt state touches the walls of the barrel, okay, we have shear stress at the places where the polymer touches the walls of the barrel. So in these cases, okay, because it touches the walls of the barrel, we have friction and we have high shear stress. And essentially, because of the friction, the chains that come in touch with the walls, these are the walls, okay? These chains are highly oriented, okay? So because they are highly oriented at the edge, we have this skin, different kind of orientation of the chains at the skin, okay? That is the upper parts here, compared to the core, where the polymer does not face any problems with having a different speed profile. So the front profile of the flowing melt completely goes uninterrupted towards the front. So in this case, we have no shear stress. And in this case, we have a random orientation. So the core has random orientation and the skin has a high degree of orientation. And that is why we say that injection molded materials generally show a skin core structure, okay? The degree of this flow-induced orientation depends on a number of parameters. On the melt viscosity, where the viscosity we already have discussed, it depends on the molecular weight of the polymer and also on the temperature, okay? And also it depends obviously on the shear stress that we just said, okay? If the shear stress is very high at the parts of the polymer that essentially touch the walls, while the shear stress is very low at the middle. And sometimes the injection molded materials display this orientation that is called fountain orientation, where essentially, again, I repeat, it's oriented chains here to the sides, and here in the middle, we have chains that look like that. Okay. Yes, we can inject in two different regions in order to have different types of materials in different sequences. Okay, it's not that complicated or important. You can see here that we have one injection molder and the second one. Okay, and we first inject, let's say, from injection molder number one, and then we fill with the second one. So we give a characteristic, let's say, multi-component structure to our material, okay? Gas-assisted injection molding is a process where essentially when you hear gas involved in polymer processing we generally use in order to fabricate hollow parts. Only in the case where we fabricate very thin layers, we use very thin films. We use gas in order to make our polymer expand towards horizontally. So in this case, where we have gas-assisted injection molding, we fill our plastic, okay? We fill our polymer mold, and then we inject with the air, so the polymer goes to the sides. And then we inject some more material, or we leave the material as it is, okay? Yeah, this is how it's called. Now, another technique, now we move on from injection molding, and another technique is called vacuum forming, okay? Vacuum forming is a technique that we essentially heat up a polymer sheet, okay? In this case, we use a polymer sheet, and we heat the polymer just above its glass transition temperature. In vacuum forming, we do not want temperatures up to the melting point. We just want up to the glass transition, okay? So then we lower this down and we draw the vacuum from below, and by using this positive mold, we create these type of materials, okay? Thermoforming is quite big in the industry, and you can create generally a large number of products, relatively simple as well. And finally, we have rotational molding. In this case, what we do is that we put the pellets within a rotomolder. This is a holder that looks like that, like a heated hollow mold, essentially. We have a heated hollow mold. So we put the polymer pellets in there, we melt them. And then we rotate our mold in order to make the polymer touch all the walls of the mold, okay? So we perform complex and very fast rotation of the mold in order to make the polymer touch the walls of the mold, and then we cool the mold very fast, okay? And if we cool the mold very fast, we solidify our polymer and we create these materials that take the shape of the walls of the mold, okay? So we need the mold to continue to rotate at all times during the heating phase in order to avoid any deformation. And also we need the mold to completely move also during the cooling process. So it's a process where this mold, after closing it, it completely moves all the time in order to make the polymer melt, touch the walls, and then solidify there. And you can see some roto-molded products as well. And now that's a final graph. Let me show you this before we go to a break. Essentially, if we have a semi-crystalline material, which we said that this part, this is the glass transition we said, and this is the melting point. Below the glass transition, generally, we are in the glassy state, okay? So generally, below the glass transition, we do not do any type of polymer processing. And in this case, at these temperatures, is a temperature range where we use or demold our polymers. So this is after polymer processing. Now, at temperatures between the glass transition and the melting point, the techniques that we use are vacuum forming and bottle blowing, okay? We already explained why. We don't want the material to be in a flowing state in order to go air in there, in order to create hollow parts. And finally, for temperatures above the melting point, we said that we use techniques such as extrusion, injection molding, and roto molding. Okay? Take a 10-minute break now, and we will resume with multiple choice questions for revision. Okay? See you in 10 minutes. And also, any questions, please feel free to ask me. Okay, so let's get started with the second part of today's course, and as I told you, we will be doing some multiple choice questions just for revision on the sessions 5 and 6. View single page, yeah. So I have prepared a couple of relatively simple questions. With some of the important parts of what we discussed the other days, okay? I should point out that in this case, in this multiple choice question test, there will be questions which might have more than one correct answers, okay? Now, in the final exam, you will have multiple choice questions, but there will be only one correct answer, okay? Also, on another note regarding your final exams, I already gave you the point about you using units every time, but also please try to remain as clean as you can when you're writing. Use don't mess up your script. Don't do a lot of of mistakes by I don't know, making black really large areas of your scripts and so on, because you do not help yourself with the way you present your papers, and you do not help the one that's marking your papers. Okay, so please try to be as clean, as cohesive, and as neat as you can when answering your questions. You will have enough pages in your exam scripts in order to fill them. Okay, so let's get started with these multiple choice questions, and we go to question number 1. Which polymer processing technique is most commonly used for the production of multi-layer films for food packaging? Vote question 1, A, B, C, and D. Multi-launch vote. And then I go to the materials. Sorry, guys. I wish I could have you all in one. Give me a second. The Wacom stopped working. I wish I could have you all in one group. Okay, let's go to materials. Sorry, guys, materials. I just saw a question. GJ, I'll answer it once we finish. Vote question 1, A, B, C, and D. It's relatively simple. I'll give you 1 more minute and we will continue. Okay. Let me end the vote. End it. Okay, for the materials group, the majority said co-extrusion. And for the polymers group, have a look. Indeed, over there, the vast majority also said co-extrusion. Indeed, co-extrusion is the correct answer. You remember saying that If we need to produce multi-layer films, the most straightforward way, the most commonly used way, is co-extrusion. So we use 2 or 3 or 4 extruders in line, okay, and we extrude in the same path essentially, okay. So we extrude if we have extruder number 1, which is red, and we have extruder number 2, which is second polymer, okay. We extrude from the blue side over there, and we extrude from the red side over there, and then they're combined, and we form these, let's say, multi-layer films, okay? So co-extrusion is the only correct answer in this case, okay? Question number 2. If we want to prepare a thick polymer sheet by melt processing, which of the following demands need to be satisfied? Low melt flow index, low viscosity, high viscosity, or high molecular weight? Let me end the previous vote and vote question 2, A, B, C, and D. Done. Initiate vote. And we go to materials. Question 2, A, B, C, and D. Okay. One more minute. Okay, let me have a look. Okay, let me end the vote. For the materials group, the vast majority of you said that high viscosity is the correct answer, but some of you said also low melt flow index, and also some of you even said low viscosity. Let me see at the polymer group, and I'll give you the answer. So for the polymers group, indeed, the vast majority found that there is more than one correct answer. Most people said A, low melt flow index, and C also was a quite popular choice. In this case, let's have a look what we need to do if we want to prepare a thick polymer sheet. Okay, you remember this graph that we had of thickness, let's say millimeters, over melt flow index, grams per 10 minutes. Okay, you remember that we had these values here, and then it was looking like that. Okay, And we were saying that if we want to have high thickness, so a thick polymer sheet, we have a low melt flow index. But we know that the melt flow index is proportional to the inverse of viscosity. Okay, so low melt flow index is correct answer. Given that a low melt flow index is related to high viscosity, so C is also correct because we have this relationship here. Okay, and finally, because we have high viscosity, generally the materials with high molecular weight give high viscosity. So D is also correct. Okay, so that is these are the three correct answers in this case. What would be a suitable processing method to fabricate elastomer blends? Okay. Question number 3. A, B, C, and D. Go to materials. Okay. Let me see what you answer. We want to blend 2 elastomers, okay? One more minute. Let me see how you're doing. Okay. Aristotle, that's a nice nickname. In Greek, it's Aristotelis. Okay. Quite shared opinions. Okay, let me end the vote for materials and vote. And so the majority of materials said latex mixing is the correct answer with 56 votes. Some of you said injection molding also 31%, or melt mixing as well, or powder mixing. Okay. So it's quite shared, the opinions. Let me go to the polymers, see if they did any better. Again, here it's the results are quite shared. The majority, 50% of you said latex mixing is the correct answer, while some of you also said injection molding or melt mixing. Now, let's have a look and discuss what this question says. So we want to fabricate elastomer blends, okay? First of all, we're talking about elastomers. What are elastomers? We already discussed extensively that elastomers are amorphous materials. And what is the feature of amorphous materials? They do not melt. Okay? If they do not melt, then we cannot use melt mixing or powder mixing because these operate at temperatures higher than the melting point. So the polymer needs to be in a molten or liquid, let's say, form. Okay? The same applies for injection molding as well, okay? So in this case, the correct answer is latex mixing, okay? By latex mixing, we create what we said, we create these aqueous emulsions, okay? So these are water-based emulsions. And latex mixing takes place, okay? So latex mixing would be a suitable processing method to fabricate elastomer blends. Question number 4. Which polymer processing techniques take place at temperatures below the melting point? Vote. Question 4. A, B, C, and D. Vote. Okay. After we finish, I'll upload these multiple choice questions and the notes for the last section onto QM+, okay? One more minute. Okay. So from materials group, majority of you said D is the correct answer. Some of you also said B is the correct answer. And from the polymer group, the vast majority, 70% of you said D is the correct answer. Indeed, D is the correct answer. Both blow molding and vacuum forming need temperatures where we don't have the polymer in a liquid state, the molten state, but we need temperatures above the glass transition temperature. So in this case, the polymer, the processing temperature is between the melting point and the glass transition. Okay. I haven't introduced you to shear thinning, so let's ignore this question and let's go to this one. If the volume fraction of the minority phase polymer is ranging between 33 to 37 volume percent, what would you expect the arrangement of the polymer to be, of the copolymer, in a copolymer? Okay, so we have a copolymer and we know that the minority phase has this percentage. What would you expect the arrangement to be? This is question number 6A. Oh, come on. B, C, and D. Let me go to materials. Question 6. B, C, D. Okay. I'll give you, I don't know, 30 more seconds for that one. It's very easy. Sorry. Okay, indeed, you all got it correctly. I don't even need to check the other group. So indeed, we have this really unique shape, this gyroid, or double diamond, as sometimes people call it, but gyroidal. It's the most appropriate way, where we have this bicontiguous structure. We already talked about that. This bicontiguous structure means that if we have continuous unit cells, like the one that I'm trying to draw here, okay, so if we have this structure, use blue. So if we have this structure here, and we have continuous unit cells, we can go from the one phase to somewhere else in alpha phase, if this is alpha phase. And with red, we have the beta phase. So we have a bicontiguous so we can go anywhere within a second unit cell by only passing through alpha phase or only passing through beta phase without switching between phases, okay? Question number 7. If we mix an epoxy matrix with rubber nanoparticles, what do we usually aim for? Higher stiffness, higher toughness, higher thermal stability, or higher thermal conductivity? Materials, vote, question 7, A, B, C, and D. Initiate vote. We go to polymers. vote question 7, A, B, C, and D. Let's see. Two more minutes, or 1 more minute, let's say. 1 should be enough. Quite divided opinions. Okay, I don't see any more answers. Oh no, I see some answers from polymers. 30 seconds. Okay. Okay, so the majority of you said, 50% of you said B, but there are quite a lot of votes with different types of answers. Okay. Amending this one for polymers. Let me go to materials. The majority of you said, 69% of you of the materials said C, thermal stability. Yes. Okay, let's have a look at what options do we have. Let's start with higher thermal stability and thermal conductivity. In terms of thermal conductivity, the two polymers, generally polymers have very low, so if we mix epoxy with rubber, it won't do anything else. It won't give us any benefit, okay? So generally, this will not lead to higher thermal conductivity. Thermal conductivity of polymers is usually in the order of 0.3 to 0.5 watt per meter Kelvin. Very low. So D is not the correct answer. In terms of thermal stability, some of you answered, epoxies are very thermally stable, okay? So even if rubbers are generally thermally stable themselves as well, it's not expected that that they will give us higher thermal stability. So mixing an epoxy with rubber nanoparticles is not our target to increase the thermal stability. And now let's have a look at whether we want higher stiffness or higher toughness. Okay, let's have a look at the two materials. We have the epoxy matrix, which is stiff. Okay, we know that flexible epoxies are stiff. What does stiff mean? It means that it has high modulus and low elongation. So if we plot the stress strain curve, sigma, let's say megapascals, and the strain, usually in percentage, For an epoxy matrix, it will look like that. Okay? That is for epoxy. Now, what do we know about elastomers? Okay, about rubbers. We know that rubbers generally are soft. So what does soft means? It means that they have low stiffness. And also they are very flexible, okay? They can elongate several times their original length, okay? High elongation. So if we mix an epoxy matrix with rubber materials, the stress strain curve will look like that, okay? So this is epoxy plus rubber. It fails here, okay? We already said very briefly that toughness is the area under the stress strain curve, okay? So as you can realize, the toughness in this region is much higher than the toughness in this region. So we usually aim for higher toughness, okay? So B is the correct answer. In order to reinforce an epoxy matrix and induce higher stiffness, we need something that is more stiff than epoxies. And it is generally very, very difficult to do this by blending epoxies with something else in terms of polymers, okay? And that is, if we want to increase the stiffness of epoxies, we usually blend them with nanoparticles or short fibers and so on, which have moduli and strengths much higher than the ones of epoxies. Question number 8. Which parameters enable control of the phase structure in block copolymers? Vote question 8, A, B, C, and D. Okay, 2 minutes. Let me have a look. Okay, let me end the vote. Majority of you got it right for the polymers group. Let me check the materials. Indeed, the materials also, majority got it right. Vote and vote. Yes. So you remember we drew the, let me use red. We drew the phase diagram of a block of polymers, okay, and it looked like that. We have different types of something like that, okay. And you remember, if you remember, this is a phase diagram. This is a disordered region, and anywhere within this region we have order, okay. We have these nanoscale regions of very high precision. And if you remember, we talked about generally the factors that affect this phase diagram, which are x times x, which is in degree of polymerization, x, the Flory-Huggins interaction parameter, he, and also the composition of the copolymer, where is usually shown with A or FA or VFA. Okay, so all three are indeed correct. Okay, 37. Okay, well, let's do just this one. Which polymer processing technique, polymer and processing technique would you select for the manufacturing of a yogurt container? Final question. Question number 9. A, B, C, and D. Vote. Question number 9. A, B, C, and D. 2 minutes. Thirty seconds and we're done. Okay, sorry, I'll end it now. Just to the vast majority of the polymers group, 76% said D is the correct answer. And let's go to the materials group. Come on. The vast majority said C is the correct answer. Well, I have to say that the answer is in the middle. Both answers are correct. Both Polypropylene and vacuum forming at temperatures lower than the melting point can be used in order to manufacture a yogurt container, and also PET and injection molding can be used for the fabrication of a yogurt container. Okay, so with that, we will conclude for today. That's the part of poly processing. I will see you on Thursday with going on to a new section, rubber and fluid session on polymer physics. Okay. Thank you very much for your attention. Enjoy your evening and see you on Thursday. Bye, guys.